On March 14, 2026, a network of GPS stations stretching from northern California to southern Oregon recorded something that seismologists had been watching for with growing concern. The ground beneath the Pacific Northwest moved, not during an earthquake, not from volcanic activity. The movement was slow, steady, and sustained over a period of 11 days. By the time it stopped, sections of the coastline had shifted horizontally by up to 4 centimeters, roughly an inch and a half, in the direction of the Pacific Ocean. I'm hosting Space Horizon, where we cover major scientific developments without the exaggeration. By the end of this video, you'll understand exactly what type of geological event caused this movement, why it's different from normal tectonic plate motion, and what it tells scientists about the stress building along the Cascadia Subduction Zone, the fault system capable of producing a magnitude 9 earthquake. Let's start with what actually happened. The west coast of North America sits on the North American tectonic plate. Just offshore, beneath the Pacific Ocean, lies the Juan de Fuca plate, a smaller oceanic plate that's being forced underneath the North American plate, in a process geologists call subduction. This happens continuously at a rate of about 4 centimeters per year, roughly the same speed your fingernails grow. Under normal conditions, this motion is locked. The two plates press against each other with enormous force, and friction keeps them from sliding smoothly. Instead of moving continuously, stress builds up over decades and centuries until it exceeds the strength of the rocks holding the fault in place. When that happens, the fault suddenly slips, releasing all that accumulated energy at once in a massive earthquake. But there's another process that happens along subduction zones, one that releases stress without a major earthquake. It's called slow slip, and it's exactly what the GPS network detected in March 2026. During a slow slip event, the locked section of the fault releases gradually over days or weeks, instead of rupturing suddenly in seconds. The ground moves, but slowly enough that nobody feels it. No buildings shake, no alarms go off. The only way to detect it is through precision instruments that can measure millimeter-scale movements of the Earth's surface. Slow slip events have been observed along the Cascadia Subduction Zone before. They happen roughly every 14 months on average, and scientists have been monitoring them closely since GPS technology became sensitive enough to detect them in the early 2000s. What made the March 2026 event different was the amount of movement and where it happened. Most slow slip events along Cascadia occur deep beneath the surface, 25 to 45 kilometers down, in a zone where the plates are warm enough to slide past each other without completely locking up. These deep events release stress gradually and are generally considered a pressure relief mechanism that might actually reduce the likelihood of a major earthquake by preventing stress from building to critical levels. The March 2026 event was different. GPS data and seismic monitoring indicated that the slip occurred at a shallower depth, somewhere between 15 and 25 kilometers beneath the surface. That's within the zone that geologists call the seismogenic layer, the depth range, where rocks are cool and brittle enough to rupture suddenly in a major earthquake. And the total amount of slip, up to 4 centimeters over 11 days, was significantly larger than most previously recorded slow slip events in this region. Dr. Harold Tobin, the director of the Pacific Northwest Seismic Network at the University of Washington, told reporters in late March that while slow slip events are normal and expected, the location and magnitude of this particular event were unusual enough to warrant close attention. His team immediately deployed additional temporary seismic sensors along the coast to monitor for any signs of increased earthquake activity that might follow. Here's why that matters. Slow slip events don't directly cause major earthquakes, but they can trigger them. When one section of a fault slips, even slowly, it transfers stress to the adjacent sections that are still locked. If those sections are already close to their breaking point, the added stress from a slow slip event can be enough to push them over the edge. This has happened before in other subduction zones around the world. In 2011, a slow slip event was detected offshore from Japan about 2 weeks before the magnitude 9.1 Tohoku earthquake struck. Scientists reviewing the data afterward concluded that the slow slip likely contributed to the timing of that rupture, though it wasn't the sole cause. The plate boundary was already loaded with centuries of accumulated stress. The slow slip was simply the final push. The Cascadia Subduction Zone has not produced a major earthquake since January 26, 1700. We know the date precisely because Japanese historical records documented a tsunami that struck the coast of Japan with no corresponding earthquake felt there, which could only have been caused by a massive rupture on the other side of the Pacific. Geological evidence from coastal marshes, tree ring studies, and offshore sediment cores all confirm that a magnitude 9 earthquake occurred along Cascadia that night, rupturing a fault segment stretching from northern California to British Columbia. That was 326 years ago. Paleoseismic studies, which look at the geological record of past earthquakes preserved in layers of sediment and soil, indicate that major Cascadia earthquakes happen on average every 300 to 500 years. Some intervals are as short as 200 years. Some are as long as 800. The current gap of 326 years is well within the historical range, but it's long enough that stress along the fault has had more than 3 centuries to accumulate. Scientists estimate that the locked portion of the Cascadia Fault has built up between 15 and 20 meters of slip deficit. That's the total amount the plates would have moved if they were sliding smoothly, but haven't because they're locked together by friction. When that section finally slips, all 15 to 20 meters of motion will happen in a matter of minutes, generating an earthquake comparable in size to the 2011 Tohoku event or the 2004 Sumatra earthquake, both of which were magnitude 9 or greater. A magnitude 9 earthquake rupturing along Cascadia would produce violent shaking lasting between 3 and 5 minutes across a region that includes Seattle, Tacoma, Portland, Eugene, and Victoria. Coastal areas would experience ground acceleration strong enough to cause widespread damage to unreinforced buildings and infrastructure. And within 15 to 30 minutes after the shaking stopped, a tsunami generated by the sudden uplift of the seafloor would strike the Pacific Northwest coast, with wave heights potentially exceeding 30 meters in some locations. The population at risk includes roughly 7 million people in Washington and Oregon alone, plus additional millions in Northern California and British Columbia. Many of the region's critical infrastructure systems, including bridges, highways, water treatment facilities, and natural gas pipelines, were built before modern seismic codes were adopted and have not been fully retrofitted to withstand shaking of this magnitude. So when a slow slip event happens in the shallow part of the fault zone, the part that will eventually rupture in the next megaquake, scientists pay attention. Not because the slow slip itself is dangerous, but because it's a reminder that the system is active, stress is accumulating, and the conditions that will eventually produce a major earthquake are developing in real time. The March 2026 event prompted the U.S. Geological Survey to issue what's called an information statement, not a warning or prediction, but a formal communication to emergency managers and public officials, noting that the short-term probability of a major earthquake had increased slightly above background levels. Specifically, the probability of a magnitude 7 or greater earthquake occurring within the following 2 weeks was estimated at roughly 1 in 200, compared to a normal background probability of about 1 in 3,000. That's still a small number in absolute terms. A 1 in 200 chance means it almost certainly won't happen. But it's enough of an increase that officials in Washington and Oregon sent out reminders to residents about earthquake preparedness. Make sure you have emergency supplies. Know where your gas shutoff valve is. Identify your evacuation routes if you live in a tsunami zone. Review your family communication plan, standard public safety messaging, delivered calmly, designed to encourage preparation without causing panic. And then the 2-week window passed with no major earthquake. The elevated probability returned to baseline. Life continued, which is exactly what happens with the vast majority of slow slip events. They occur, they're recorded, they're studied, and nothing dramatic follows. The system releases some stress, and the clock keeps ticking toward an eventual rupture that might happen next year, or might not happen for another 200 years. But here's the part of this story that's worth understanding clearly. The fact that this particular slow slip event didn't trigger a major earthquake doesn't mean the next one won't. Every slow slip event is a test of how much stress the locked portion of the fault can handle. Each one brings the system closer to the point where accumulated strain exceeds the strength of the rocks holding the fault together. Seismologists describe this using a concept called the seismic cycle. A subduction zone starts with a major earthquake that releases centuries of accumulated stress. Immediately after that quake, stress along the fault is low. The plates are no longer locked because the rupture allowed them to slip. Over the following decades and centuries, the plates gradually lock up again as friction stops their motion, and stress begins to accumulate once more. Early in the cycle, slow slip events are common and relatively safe because there isn't much stress built up yet. Late in the cycle, when the fault has been locked for centuries and stress is approaching the breaking point, slow slip events become more dangerous because they're happening in a system that's primed to rupture. Cascadia is late in its cycle. The 1700 earthquake released the fault. The 326 years since then have been spent reloading it. We don't know exactly how close the system is to failure because there's no instrument that can measure that directly. What we can measure is the slip deficit, the GPS detected motion during slow slip events, and the patterns of seismic activity in the region. All of those measurements are telling scientists the same thing. The fault is locked. Stress is accumulating. Slow slip events are transferring some of that stress, but not enough to prevent an eventual major rupture. And when that rupture happens, it will be one of the largest natural disasters in North American history. The question isn't whether a Cascadia megaquake will happen. The geological record is clear that these events occur regularly over timescales of centuries. The question is when. And the honest scientific answer is that we don't know. Earthquake prediction, in the sense of being able to say with confidence that a specific earthquake will happen on a specific date, remains beyond current scientific capability. What we can do is identify patterns that suggest elevated risk. The March 2026 slow slip event was one of those patterns. The location, the depth, and the amount of movement all indicated that the shallow locked zone of the fault is active and accumulating strain. That doesn't tell us when it will fail, but it tells us the system is behaving the way we'd expect a system to behave in the late stages of its seismic cycle. There are other indicators scientists watch as well. One is the pattern of small earthquakes in the region. Cascadia is generally a quiet subduction zone compared to others around the world. It doesn't produce frequent moderate quakes the way the San Andreas Fault in California does, but it does produce small tremors, particularly in association with slow slip events. These tremors are too small to feel but show up clearly on seismometers as a kind of seismic rumble that can last for days. During the March 2026 slow slip event, seismic stations recorded an increase in tremor activity along the Washington and Oregon coast. That's expected. Tremors and slow slip are linked. The concern would be if tremor activity suddenly stopped, because in some other subduction zones, a cessation of tremors has preceded major earthquakes. The idea is that if the fault is so locked that it can't even produce tremors anymore, it might be on the verge of a catastrophic failure. So far, that hasn't happened along Cascadia. Tremors are still occurring. Slow slip events are still happening. The system is stressed, but not yet at the breaking point. The challenge for scientists and policymakers is communicating that reality to a public that wants clear answers. Is an earthquake coming soon? Should people be worried? Should they leave the region? The responsible answer is more nuanced than a simple yes or no. A major earthquake is coming eventually, possibly within the next few decades, possibly not for another century or more. People living in the Pacific Northwest should be prepared the same way people in California are prepared for San Andreas earthquakes, or people in Japan are prepared for subduction zone quakes. That means having emergency supplies, knowing evacuation routes, retrofitting buildings where possible, and understanding that when the shaking starts, you'll have only seconds to take cover and minutes to get to high ground if you're in a coastal tsunami zone. It doesn't mean living in constant fear or abandoning the region. Millions of people live productive lives in earthquake-prone areas all over the world. The key is preparation and acceptance of risk, not panic or denial. The March 2026 slow slip event served as a reminder of that risk. The ground moved. Scientists monitored it. The probability of a major quake increased slightly and then returned to baseline. No disaster occurred, but the system remains active, stress continues to build, and the next slow slip event, or the one after that, or the one a decade from now, could be the trigger that finally releases 326 years of accumulated strain. That's the reality of living on an active tectonic boundary. The Earth beneath you is not static. It's moving, slowly and constantly, accumulating energy that will eventually be released. The tools we have can measure that motion and identify patterns that suggest increased risk, but they can't predict with certainty when the release will happen. What they can do is give us time to prepare. Building codes have been updated. Tsunami evacuation routes have been mapped. Emergency response plans have been developed. Public awareness campaigns have educated millions of residents about what to do when the shaking starts. None of that will prevent the earthquake, but it will save lives when it happens. The West Coast moved in March 2026. It moved slowly, over 11 days, in a way that released some stress without causing damage. Scientists monitored the movement, analyzed the data, and determined that while the event was unusual, it didn't represent an immediate threat. The heightened probability window passed. The region returned to its baseline state of uncertain waiting, and the fault is still locked. The plates are still pushing against each other. The stress is still building. And somewhere in the future, whether that's next year or a century from now, the Cascadia Subduction Zone will do what it has done every few hundred years for millennia. It will rupture. The ground will shake for 3 to 5 minutes, and the Pacific Northwest will face the megaquake that geology has promised and that science cannot yet schedule. Here's what you should take away from this. The March 2026 slow slip event was real, measurable, and scientifically significant. It occurred in a part of the fault that will eventually rupture in a major earthquake. It temporarily increased the probability of that earthquake happening in the short term. And then it passed without incident, which is what happens with most slow slip events. The fact that it didn't trigger a megaquake this time doesn't mean the risk has disappeared. It means the clock is still running. The system is still active. And the best thing people in the Pacific Northwest can do is treat this as a reminder to check their preparedness, review their plans, and make sure they're ready for an event that might not happen for decades, but could happen tomorrow. If this kind of straight-talk science coverage is what you're looking for, subscribe to Space Horizon. We cover geological and space science discoveries as they actually unfold, with all the uncertainty that real science involves. Drop a comment and tell me, if you live in an earthquake-prone region, what's the one thing you've done to prepare? I'm genuinely curious what people prioritize. Next time, we're covering what scientists found beneath Yellowstone that suggests the supervolcano's magma chamber is larger and shallower than previous estimates indicated. Thanks for watching. I'll see you at the next horizon.